Section 16.3 is about colligative properties. So we'll talk about what a colligative property is and then look at different examples of colligative properties. So there's a couple definitions or a couple components that you should know in regards to colligative properties. The first is that these are properties of mixtures, or properties, and to be more specific, these are properties of solutions. And remember, we said solutions are homogeneous mixtures. So homogeneous and solutions mean the same thing. Okay? So these are properties of solutions. Colligative properties are properties of solutions. They also depend on the amount of solute in the mixture. So what does that actually mean? So if we have a little bit of solute, we won't have a very prominent colligative property. If we have a lot more solute, then the colligative property is going to be more significant. And so we'll talk about some of the different types of colligative properties. The first one that we'll discuss, and we'll do calculations with it as well, would be vapor pressure lowering. So one of the colligative properties is vapor pressure lowering. So if we review what vapor pressure is, you guys talked about vapor pressure in the gas unit. So remember, and I'm going to draw this diagram here. Remember when we were talking about boiling points when in regards to the gas unit that we did, and we said that if we had like a pot with a lid on it, so something in a closed container, and let's say we had water in this pot and it was sitting on a flame, over time, if it's sitting on a heat source, so let's say it's sitting on a flame, over time these liquid water particles would get enough energy to start to evaporate, and when they would evaporate, they would create gas. Now, vapor pressure, by definition, is the gas above a liquid. Now, something that is able to evaporate very easily will create a lot of vapor pressure. Something that doesn't evaporate as easily, you're not going to have as much gas created in this container. So when we have a mixture, it actually becomes harder to evaporate. So if it's easier for you to think about vapor pressure in terms of evaporation, vapor pressure lowering just means that it becomes harder to evaporate. The mixture becomes harder to evaporate. Now, if we think about why that is, if we were to dissolve, let's say, salt or NaCl, and we put that in water, water we know is a liquid that can evaporate, but salt is a solid. Even though it dissolves in the liquid, salt doesn't evaporate. If we have salt on the table, it's not going to all of a sudden evaporate into gas. So when we make this mixture, we have some things that are going to be easily evaporating, like water, and we have other things that are not going to easily evaporate. So one of the issues when we have a mixture is that it's going to be harder for this to evaporate because we would have to evaporate the salt, which is not going to happen, not likely to happen, and we would also have to evaporate the water. Okay, so the amount of gas that we'd be able to create would be lower in a mixture than if we just had water by itself. Okay, again, the more salt we add, the more harder it's going to become to evaporate. Okay, the next one that I'll talk about is, there are three colligative properties. Vapor pressure lowering is the first one. The second one we'll talk about is boiling point elevation. Okay, so what that means is it becomes harder to boil. So mixtures are harder to boil than if you just had water by itself or the solvent by itself. So one thing to keep in mind for colligative properties, we're comparing these kind of new properties of the mixture to the properties of the solvent by itself. So if we have that salt water mixture, we know water, pure water by itself, if we just had water and it was not a mixture, we know water normally boils at about 100 degrees Celsius. Well, if we have a salt water mixture, this might actually boil at, let's say, 104 degrees as an example. Okay, now depending on how much solute we add, if this was a lot of salt, then that might have a higher boiling point. If we only added a little pinch of salt, then it might only boil a little bit higher than 100. So again, we said colligative properties, they depend on the amount of solute you have. The more solute you have, the higher the boiling point would be. The lower the solute you have, the closer to the normal boiling point that boiling point should probably be. But in any event, a mixture is always going to be harder to boil than if it were just the solvent by itself. The reason why that would be is in order for something to boil, we have to create vapor pressure. And remember, we just said the vapor pressure is normally going to be lower than usual. So if we're not creating enough vapor pressure, it's going to take a lot of time for us to get the vapor pressure we need to get it to boil. So it's because it has to sit on the flame for longer, that boiling point is going to be a lot higher than it normally would be. Okay. And these are where you guys did the different calculations to figure out the boiling points and freezing points. Okay. The last colligative property, so the first two were vapor pressure lowering, boiling point elevation. We have freezing point depression is the third one. Okay. So freezing point depression just means that it becomes harder, a mixture is harder to freeze. Okay. So if we take an example, we have, let's say we had the salt and water. And that's a mixture, and we just had pure water by itself. We know pure water boils or freezes at 0 degrees Celsius, but a salt water mixture may freeze at, let's say, negative 1.5 degrees Celsius. So the freezing point would have to be lower than if it were just water by itself. Now this is the property that they use when you have salt trucks that put down the salt solution before it's supposed to have an ice storm or it snows. And the reason behind that is if water normally freezes at about 32 degrees Fahrenheit, by putting the salt down on the roads, as soon as the snow or the ice hits the road, it's going to form a salt water mixture. And now that mixture would have to freeze lower than 32 degrees. So if the outside temperature is only about 30, 29, 28, somewhere around that range, then the mixture may actually have to be much lower in order for it to freeze. So as an example, let's say it's supposed to snow and the outside temperature is going to be about, let's say, 28 degrees. So it's definitely cold enough for water by itself to freeze. But what the salt trucks will do is they'll put the salt down in the salt solution. So as soon as the snow hits the ground, that temperature is going to have to be much lower. So you might have to have outside temperatures of 15 degrees to get the mixture to freeze. And if it's not going to be that cold, then it stays slushy. So that's kind of one example of how we would use the advantages of having a mixture to have lower freezing points than normal. All right. So now if we move on to the different calculations. So for each of the colligative properties, there are calculations that we can do to figure out what the new property would be. So if we start with the first one, we're going to start with vapor pressure lowering. You guys may not have done this calculation, but I'm going to do it on this video just in case it gets thrown on the test. Okay. So there is a way for us to figure out exactly how low the vapor pressure of a mixture is. So if we look at an example, and I'm going to kind of make these numbers up, but for your test purposes, they'd have to give a lot of these numbers to you. In order to calculate the vapor pressure, we would need to know something called the mole fraction. And for whatever reason, they use the letter X to represent the mole fraction. Now, when we calculate the mole fraction, what's important for us to calculate is the mole fraction for the solvent. So I'll write out what the equation is. So we want to know the moles of the solvent over the moles of the solvent plus the moles of the solute. So in other words, what we're basically trying to figure out is what percent of the mixture is the solvent. So how close is the solvent to being just pure with no solute in it? So I'm going to put a bunch of numbers up here. So let's say we have 3.5 moles of NaCl, and we have 7.5, call this 2.5 moles of NaCl and 7.5 moles of H2O. Okay. Well, we know the larger number is going to be our solvent. So because the 7.5 is clearly bigger than 2.5, this information is for our solvent. This one is the lower number. This is going to be our solute. So if we plug that into our equation, we would just do moles of the solvent, which is this guy, so 7.5 over these two added together. So the solvent plus the solute. Okay, so we would end up with 7.5 over 10. okay, which is 0.75. Now for the mole fraction, it is perfectly fine to leave it in terms of a decimal, which is fine. So the way that we would interpret 0.75, what that means is this mixture is about 75% solvent. It's not 100% solvent, but it's about 75% solvent. So the way that we would use that number is we would then multiply it by what the vapor pressure should be. So let's look at what that would look like. So, and I'm going to make this number up, but they should give it to you on a test or quiz. Let's say pure water, because remember water was our solvent. Let's say pure water has a vapor pressure of, let's say, 1.5 atmospheres. Okay? So if this were 100% water or 100% solvent, we would expect the vapor pressure to be 1.5. We don't have 100%, we only have about 75%. So the way that we would calculate vapor pressure lowering is we would take our mole fraction, okay? So I'll just write it out here in words and then we'll plug the numbers in. So we would take our mole fraction, and it's the mole fraction for the solvent, okay? And we would multiply that by the normal vapor pressure. Normal VP. Okay. So we take the solvent mole fraction, multiply by the normal vapor pressure, and that would give us the new vapor pressure. Okay. So if we do each of those steps, so our mole fraction was the 0.75 that we calculated. The normal vapor pressure, that's when we have 100% solvent, so we have no solute at all. That should be given to you, so that was 1.5. Okay. So another way to interpret this is if this is what it is when it's 100% solvent, we want to find out what is it when it's just 75. So we're only going to be able to get 75% of that number because we don't have a pure solution, we don't have a pure solvent anymore. Okay, so we get about 1.125. That would be our new vapor pressure. So if it's pure solvent, so it's not a mixture at all, we should get 1.5. We're not able to get all of that 1.5 because we have a mixture. And so we take the amount of solvent, instead of 100% solvent, we actually only have about 0.75%, or we only have about 75% of the solvent. So we're only able to get about 75% of this number. So our vapor pressure goes from being 1.5 if it were not a mixture to now it being a mixture, we're only able to get about 1.125. Let's do one more example of that before we move on to the boiling and freezing points. So let's say we had 5.0 moles of KBr and we had 10 moles of H2O. So again, the smaller numbers are solute, larger numbers are solvent. So if we want to do our mole fraction, we want to do moles of the solvent. So we would do 10 moles on the top, and we want to do the two added together, solute and solvent together. So 10 moles plus 5 moles. Okay? So we get 10 over 15, which would simplify to 2 over 3, which is about 0.67. Okay? So that's our mole fraction is 0.67. Okay? Of that mixture, about 67% is solvent. Okay? So again, we said that water had a normal vapor pressure. So H2O's normal vapor pressure is about 1.5. So if we want to find what the new vapor pressure is, we need to take the mole fraction, and we need to take what the normal vapor pressure should be and multiply those two together. So we do 0.67 times 1.5. So we would get 1, about 1 ATM. So we normally should make about 1.5 ATM for the vapor pressure. We're only going to be able to make 1 ATM, so it's lower than it should be. All right, so then if we move on to the other colligative properties, so the boiling point elevation, freezing point depression, I'm going to write both of those equations down, and we'll go through what each of those variables mean. So and then we have this guy. Okay. So let's define what each of these variables mean. These guys here, this is the change in boiling point. Okay. When you do this calculation, it's not going to give you the new boiling point. It's going to tell you by how much it changed. So once you solve this equation, you'll have to actually do one more step to get to what the new boiling point will be, but we'll look at that in a second. This KB value, this is our boiling point constant. Okay, and this number comes from your solvent. Okay, so we're going to keep track of this. This comes from our solvent. This boiling point constant is a given number. They should give that to you. For water, the boiling point constant is 0.512, but again, they should give that number to you on your test. Okay. This M is molality. Don't get it confused with molarity, but it's molality. And to refresh our memories, molality, or little m, is moles of solute over kilograms of solvent. But molality is the concentration. So we have to know how concentrated the mixture is to figure out how much of a change is going to happen. Keep in mind that the more concentrated the mixture is, the bigger the molality number, the bigger the change is going to be on our boiling or freezing points. Okay, and then the last one, this I, is called the von Hoff factor. Okay, and this is based off of the number of particles in the solute. Okay, so this KB is for the solvent. The I, we're going to be looking at the solute. Okay, the same thing is true for the freezing point equation. The only thing that's different is your Kf would be a different value, because this would be your freezing point constant. Again, they would have to give that to you, and the freezing point constant is in terms of the solvent. Okay, and so for water, the freezing point constant is 1.86. Okay, so if we figure out how we would use this calculation, so I'll do one example for boiling point and one example for freezing point. I'm just going to erase this. So let's say we have a mixture. We take, let's say, 117 grams of NaCl in 234 grams of H2O. And that's all we have. And our answer, or our question is, what is the new boiling point? Okay. The first thing that we want to figure out is the molality. So if I would throw out the equation again, it's the change in the boiling point equals Kb times M times I. Okay, so we want to first figure out the molality. Okay? So we know molality is moles of solute over kilograms of solvent. So you might ask, well, how do I know which one is the solute, which one's the solvent? We can look at the amounts of them. This number is smaller. This would be the solute information. This number is bigger. This is the solvent. Plus, anytime we're dealing with water, water is always the solvent. So we first need to figure out how many moles this is equivalent to. So we'd have 117 grams of NaCl. Grams would have to go on the bottom. Moles would have to go on the top. And so we'd have to add up the weight of sodium and the weight of chlorine. So they add up to about 58. When we add up, sodium's 23, chlorine's about 35, so there's 58 total. When we do this division, we see that we have 2 moles of NaCl. Okay? So if we're figuring out our molality, So far, we have 2 for the top. We now need to figure out the kilograms of solvent. Well, we have 234 grams of solvent. We have to convert that into kilograms. And remember, if we're converting into kilograms, we go over 3 to the left. So this is really 0.234. Okay. So if we divide we're going to get about 10. And I rounded this, but we get about 10 for the molality. Okay, so that's going to go right here into this equation for our molality. So if we start plugging in what we have, we're figuring out the change in the boiling point. The KB, now for water, the KB is always in terms of your solvent. Our solvent is water. The KB, or the boiling point constant for water, is 0.512, but again, they would probably give this to you on the test. We just calculated the molality, that's 10. Now, I is the only thing that we're missing, and I, we said, is that von Hoff factor, and it's the number of particles that the solute breaks into. So if we look at the solute, this NaCl, okay, I'm just going to erase this. There's a couple things that we need to keep in mind for the I value. When we're dealing with solutes, we want to look at whether they're ionic or whether they're covalent for the solutes. So depending on whether they're ionic or covalent, we're going to handle them a little bit differently. Okay? For covalent solutes, remember, covalent are nonmetals. When we just have nonmetals together, they're really easy when it comes to figuring out the I value because I will always be 1. Okay? So I'll give you a couple examples of covalent solutes. We can have glucose, C6H12O6. We can have CO2. We could have NH4. All of these guys are just groups of nonmetals together. As soon as we see nonmetals or the solute, automatically we say I is 1 because these guys are going to dissolve, but they're not going to break apart. Like the carbon is not going to break apart from the hydrogen or break apart from the oxygen. They're going to stay clumped together as a group. So I equals 1. Okay? Ionic solutes are going to be when we have metals with nonmetals. Okay, so something from the left side of the periodic table with something from the right side. So a couple of examples would be the NaCl that we have, or maybe even something like MgBr2. Those are all examples of ionic solutes. And we can even look at, let's say, AlNO3. These guys are going to break apart. They're going to ionize. We say they may ionize or dissociate. So they're going to break apart, and we need to figure out how many pieces it will break apart into. Keep in mind, covalent things don't break apart. I is always 1. Ionic things do break apart, so we're going to have different numbers for that I value. So for NaCl, this is going to break apart. We can split it right down the middle. It's going to break into a sodium and a chlorine. So I would be 2. It's breaking into 2 pieces, sodium and chlorine. MgBr2, that's breaking into 3 pieces. We have Mg, Br, and another Br. So I would be 3. Okay. And then AlNO3. If we look at this guy, this is going to break into an aluminum. It's going to break into a nitrate, another nitrate, and another nitrate. So this would be I equals 4. Right? Now these nitrates, they are non-metals. We can't break them apart. Now we can separate the groups of nitrates. We have 3 groups of nitrates and 1 aluminum, so I is 4, but we can't split the nitrogen and the oxygen. Another quick way to figure out your I value, only for ionic, you can add up your subscripts. So there's technically a 3 and a 1, that gave us 4. Or a 2 and a 1 here, that gave us 3. Or a 1 and a 1 here, that gave us 2. So again, only ionics can we add up the subscripts to figure out the number of particles. So if we skip back to our problem, we have NaCl for our solute. That's going to break into 2 pieces. So our I value over here would be 2. So when we do our math, and I'm going to round this a little bit, we would end up with roughly about 10. Now what do we actually do with that number? This is not our new boiling point, that's just the change. Now once we figure out the change in the boiling point, we need to add it to the normal boiling point. Now the normal boiling point is with water. So if we know that water normally, and so let me actually write this out in words. We always take the normal boiling point of the solvent. They would have to give this to you. If it's water, they'd expect you to know that it's 100 degrees. And we add the change to get the new boiling point. Okay. So we need to know what the normal boiling point is when it's just the solvent by itself. We add in the change and we get the new boiling point. So our solvent in our example was water. So water normally boils at 0 degrees Celsius. We just found the change was 10. So our new boiling point is now 110 degrees. Okay. We would do the exact same thing if we were doing the freezing point. Okay. The only difference is, so our new boiling point is 110. When we're dealing with the freezing point, we need the exact same type of information. We would just find our change in freezing point. We need to know what the normal freezing point is, and we would subtract the change that we found to find the new freezing point. Because remember, the freezing point gets lower, so we need to subtract. So how do we need to modify our equation? So if we go back up here, the KB, that's going to have to change because this is the boiling point constant. If we're trying to find the freezing point, we're going to have to change that number. Okay, so if we want to do delta TF, we can't use this anymore because that's the boiling point. We need to use the freezing point for water, which is 1.86. The molality can stay exactly the same. The concentration doesn't change. And the I value can stay exactly the same. We're still using the same solute. Okay? So the only thing that we need to change if you're using the same mixture from boiling to freezing point is you just need to swap out the KB for the KF. So our change in freezing point for this particular example would be roughly about, let's call it 22. Okay? Normally, water freezes at 0, and water was the solvent. So when we subtract those, we get negative 22 degrees Celsius. Now, the reason why this is such a big difference or such a big change from what it should be is that our molality is very big. The more concentrated your mixture is, the more change or more effect it's going to have on your boiling and freezing points. If this number was not as big, we wouldn't have as big of a change in either our boiling or freezing points. So keep that in mind. The bigger the molality or the more concentrated the mixture, or also the more parts that the mixture can break into or the solute breaks into, the greater the effect it will have on the boiling and freezing points. And as a last example, in case they give you this and have you just compare different things and actually not calculate, let's look at this type of example. So let's say we have 3 mixtures. We have mixture 1, that is MgCl2 is the solute. And let's say we have mixture 2. Its solute is Al2O3. Okay, and then let's say we have mixture 3. That has HC2H3O2. Okay, and let's say the question is, who has the lowest freezing point? Okay. Now we have to make a couple assumptions. We have to assume that the molality is all the same for all 3 mixtures. Okay. We have to also assume that the solvent that we're using to dissolve these solutes is all the same. Okay? So if we can assume both of those things, then what does that tell us? Let's look at our equation. So we want to know who has the lowest freezing point. We know for our equation for freezing point looks something like this. Okay? So if the solvent is the same for all of the mixtures, then the KF value is all the same. So we don't have to consider that. If the KF is all the same for all of them, that's not going to help us figure out who has the lowest. The molality is also all the same for all of them, so we don't have to really worry about that. So then it comes down to just looking at the I value, or the von Hoff factor. So we would want to figure out who breaks into the most amount of pieces. Whoever breaks into the most amount of particles for the solute, that means that has the greater effect on the freezing point. And the greater effect on the freezing point means you'd have the lower freezing point. So if we look at them, this guy is ionic. It's going to break into MgClCl, or we could add the subscripts, 2 plus 1. So in this case, I would be 3 for that first one. This one's going to break into 2 aluminums and 3 oxygens, or we could add the subscripts. I is going to be 5. Now this guy over here has a bunch of pieces to it. It has more elements in it than these guys, but if we notice, these are all non-metals. So I has to just be 1. Okay? So out of all of these, this guy has the most amount of particles. It's going to have the greatest effect on the freezing point. It's going to have the lowest freezing point out of all of these mixtures. Okay, so again, the reason why that would be is the number that we would calculate for the change in the freezing point would be larger for this one because I is 5. So if it has the larger change, it's going to be the lower freezing point. For these two, if we had to rank them from lowest freezing point to highest freezing point, Al2O3 would have the lowest freezing point because it has the greatest change. And then the next one in line would be the MgCl2. And then we would have the Hc2H3O2. This one would have the highest freezing point. Now, highest freezing point means warmer. Who's warmer? This one would be the coldest because it would have the lowest freezing point. This one would have, in comparison, one of the warmer freezing points. It wouldn't have as big of a change. So they could give you kind of a qualitative question like this where they don't give you very many numbers and they ask you to rank them based off of who may have the highest boiling point, lowest freezing point, any of those types of things. Now, if we were looking at this and the question was instead, who has the lowest boiling point, we would want to look at the one that has the smallest change. Because remember, the larger the change in the boiling point, the higher your new boiling point would be because we're adding it to our old boiling point. So who has the lowest boiling point? Our answer would actually be the last one. Why? Because the I value is 1. It's not going to have as big of a change on the boiling point. It's going to have a lower boiling point in comparison to these other two. And then MgCl2 would be kind of in the middle. And the Al2O3 would have the highest boiling point. Because it has the greatest change, it's going to be adding a lot more extra temperature to what the boiling point used to be. Whereas this guy would have the lowest boiling point. So just be familiar and comfortable with figuring out lowest boiling point versus highest boiling point, lowest freezing point versus highest freezing point, just when you have to look at the I values. So this could be a type of question they could ask you as well. So hopefully this helped to review colligative properties. Just remember, double check your calculations when you're doing them. Solute is the thing that gets dissolved. Usually it's in the smaller amount, and the solvent is the one that does the dissolving, and that's going to be the one in the highest amount.